So time to compute mass moment of inertia for composite parts. And so I'm going to go into my tables again and give you a little information. So this is what would be called a right cone, because its center comes perpendicular off of the base. And so we have at the base some radius r, and this would go all the way around. Here's G, so the centroid of the cone, or center of mass as it were, is at h over 4. We're understanding this cone to have, this is the center of volume, and if we have a constant density, it would be the center of mass as well. Height of the cone is h. Out of the tables, we get some nice information. The volume of the cone is pi over 3 r squared h. Okay. Ix and Iy, these are symmetrical, so they'd be the same. 3 over 80 mass times the quantity 4r squared plus h squared. And Iz, so rotating about this center line, is 3/10 mr squared. So here's my composite part. It's basically made out of 3 cones where 2 sort of don't exist. So I'll try to keep this here for a moment. And let's see, can we get that all in? Shrink that down a bit. There we go. So what is this cone? My measurements are in millimeters. So picture I had a big cone here coming down. Half of the base is 800 millimeters, so the whole base would be 1600 millimeters. R being 800. And what's happened is I did a couple of machining operations. I lopped off the top of the cone, all right, and then we countersunk a cone into the cone, all right. So if we look at this, the original cone would have gone up to, I'll leave you to check the math, but the original cone would have been 1,333 millimeters high. So from relative to here, it goes up another 333. We're cutting that off, all right? And then we countersink a 600 millimeter cone into the cone, all right? We're measuring off the base, so there's positive z going up. And so we're going to compute a couple of things. One, relative to the center axis here, z1, we're going to compute mass moment of inertia about z1, and then we're going to move it over 1.5 meters to get the mass moment of inertia at this axis z2. All right? So, and here's our density, which we'll use, no problem. So we need to find iz1 and iz2. All right? So let's just start breaking this thing down. When I see problems like this, I want to break them down into parts, just like we would do with composite parts with center of mass, volume, area, yada yada. Okay? So here is my part algebra, as I call it. Okay? So I am making this using, here's the big cone, that's 1,333 millimeters high. On an exam, we have found students absolutely stalled, unable to figure out how high this cone is. Using similar triangles, you can figure this out. I'll leave that to you, but you need to be able to do it. Okay? Given your background, you can do that. That I'm leaving for you. Then we cut off the top. Okay? As you can see, up here it's 1,000 high. So if that's 1333, it's obvious the part I'm cutting off is 333. So that's a negative, taking material away, and then I'm countersinking, that's putting a hole into this thing, and that's obviously from the picture 600 millimeters. All right, so let's think what we're going to need to do this. Okay, let's cone volumes. Why do I need the volume? So that made people maybe go, why am I doing that? Well, we need the volume of the cone because we don't have the mass of anything. We have the density of the cone. It's all one density, easy to handle, but so I need to, for every one of these cones, compute the volume, then I can multiply by the density to get the mass. This is mass moment of inertia. So I got to get volume to go get mass. No problem. So up at the top, we had an equation, pi over 3 r squared h was our equation. All right, so I've modified that, not multiplied. I modified that slightly, so everything was in millimeters. I'm dividing by 1,000 cubed to convert into meters. So here's our first cone. If we look here, the radius was 800, or it is 800, so I have pi over 3, 800 squared, radius squared, height 1333, divide by 1,000 cubed, 0.893 meters cubed. And oops, there we go. Let's just bring all of that up now. So that's where that came from. The second cone, this little bitty one, all right, its radius, if we go look up here, I'm going to bring that down a little bit, okay, at the base, the radius of it is 200 millimeters. I'll let it go up a little. And the height is 333. So we go pi over 3, base 200 squared, height 333, divided by 1,000 cubed, 0.014 meters cubed. And then we have the countersunk one. So it's pi over 3. Its base is also 200 millimeters. Square that, times the height, 600, divided by 1,000 cubed, 0.025 meters cubed. Now that we have that, multiply every one of these by 200, and we will have the mass. All right, so I'll show that on the next page. It's very straightforward, but let's just think what we can do now. All of these, this, that, and the one that was cut away, are all centered. Their center of mass goes along that z. So they're all there. We don't have to do any parallel axis theorem, moving anything from its initial center line over to the z1 axis. They're all lined up. So I can compute mass moment of inertia for z1 directly. And what's that going to be? So we're going to get the mass moment of inertia for z1 directly, and that's this equation. 3/10 mass times radius squared. All right? So I've got 3 cones that are on z1. The first cone has radius 800, and I know its mass. The second 2 have radius 200, and I know their masses. So let's finish this problem up. So, finishing this thing up, we have mass 1, just multiply by 200, mass 2, mass 3. But note, masses 2 and 3, add another little negative sign here, are material cut away. They're cutaways. All right? So the total mass is this minus that, gives us 170.91 kilograms. All right? Now, relative to Z1, we don't need the total mass. We'll need that in a moment. So we had the first cone, 3/10, mass 1, which is up here. Its radius was 0.8 meters. We'll square it. The second one, the tip which was cut off, 3/10, the mass which is up here, we're subtracting because we cut it away, 0.2 squared. And then the one that that was countersunk, 3/10 m3, 0.2 squared as well. This minus that leaves us with 34.22 kilogram meter squared. Now, let's just go back to our previous picture real quick. Once we have Z1, we want to move the axis 1.5 meters over. Not a problem. So we have this. We're going to use the parallel axis theorem. So IZ2 will be IZ1, just put that number down here, plus the total mass, that's why we computed it, moved over 1.5 meters squared. Bam. 418.6 kilogram meter squared. We're all set. We're going to do one more composite problem, and this is a flywheel. So if you think about having a machine, flywheels are used quite often. Why are they used? because once you get a machine spinning at a given speed, you don't want to have interruptions and you want it to maintain that speed. So the idea is you have a flywheel and you're going to have more mass farther away from where it's spinning. So here I have a plate, four bolt holes basically, and sort of this big tire that's out further away. Okay, and this would constitute a flywheel. So if this were here and spinning like so, all right, this is resistance to changing the speed. So the idea is you get a machine up to a speed you want, and you have a big flywheel on it because you want it to maintain that speed. So no matter what happens, it just keeps that happening. Okay, and one of the types of machines you'd put a flywheel on would be a multi-cylinder engine. So every cylinder is firing, cylinder 1, 2, 3, 4, 5. So what would be happening there is each cylinder is a force of torque, so to speak, going onto the axle to spin it around. It's not a constant torque being applied. It's as each cylinder fires. So the idea is that in between the cylinder hits, this just causes less change in the rotational speed. So that's the purpose of a flywheel, if you hadn't really thought of it before. So what I have here, let's just take a look at what this flywheel is. Plate, 4 bolt holes. The bolt holes are 1 foot off the center. And 2 feet off the center, I have this great big tire, big steel piece going around the edge. The bolt holes, the radius is 3 inches. It's 1/4 foot. So right there. And here the quote-unquote tire portion of this starts at 2 feet, ends at 2.5 feet. All right. Now for this problem, I'll note, I'll just get to that in a minute. So if we looked at this cross-sectionally, just cut this through, here we see sort of the tire end part. And so what we see is this, the tire part, this is 1 foot across. And here the center plate is a 1/4 foot. All right, so lots of mass here on the outsides. This is going through the center is the little x-axis. Here's the x prime axis. And for this problem, what I want to do is I want to get the mass moment of inertia about x prime. Why would you want that? You wouldn't. A flywheel is always going to spin against its center, but for educational purposes, we're going to compute this and we're just going to move it over there. Okay? No real practical purpose, but as we're learning, it serves an educational purpose. And we're going to be doing this in American units, so we have specific weight here, 90 pounds per foot cubed. So let's start attacking this problem. So as I always tend to do when I do these problems, I try to just kind of organize my thinking. And so I do the part algebra. So how am I visualizing this thing? So what I'm going to do is I'm going to visualize this. Oops, let me bring this down a little bit. I'm going to envision this as being a great big, viewing it from the side, big rectangle. Or from the other side, just be a great big solid disk. Okay? And then I'm going to subtract off these disks in here. Okay? And then I'll subtract off all my bolt holes that go through that little plate. All right? So this is the positive material. Then I'm taking it off, and taking it off 4 more times with the bolt holes. So that kind of organizes my work. All right? Now, if you look at what this is being made out of, everything's a disk. Okay? Those holes are disks. All right? This part I'm cutting out here, it's a disk. It's a disk. The original piece is one great big disk. All right? So relative to that, it's maybe hard to see, but relative to this x, if you were going through the center of a disk, its mass moment of inertia is 1/2 mr squared. So we're going to use lots of 1/2 mr squareds here. All right. So let's just show this table that I have for this problem. So part one was the great big disc on the outside here. All right. So what was it? It has a radius of 2.5. It has a thickness of 1 foot. All right. Based on that, I can compute volume. Volume would be pi r squared, pi times 2.5 squared times 1 foot thick. All right. That would give me volume times 90 over 32.2, because this is pounds, it's a force. I'm looking for mass. Okay, 1/2 mr squared. And that's the reason I'm doing this problem, is because people aren't used to using these kinds of units. So 90 divided by 32.2 gives us the mass of the first part, 54.88. And the unit is slugs. This is one of my favorite units. I don't know what person thought this would, because slugs are kind of gross, and why would you have a slug? I think about the little, I don't know what they are, mollusk or whatever it is. But we have 54.88 slugs. Knowing the mass, all right, going through the center of this at x, 1/2 mr squared. So 1/2 times 54.88, that's the mass. The radius, 2.5 feet. We get 171.5 slug foot squared. Exciting. Okay. So now we have these two discs that I'm going to take out. All right. Now, if you think about this, here's 1/4 foot in here. So I've got a piece on this side and a piece on that side. Each one of these is, let's see what the thickness is. Now, you'll notice I have 0.75 in here. And you may, at first glance, you'll go, well, that's not right. Because if this is 1, then you'd have 0.25, and assuming that's centered, you'd have 0.375 on this side and 0.375 on that side. Well, think about this. They're all about the same axis. Whether they're on different sides or not, the thickness, I just doubled it. So I'm going to deal with both of these pieces. So you see how I had two and I kind of grouped them together here? I'm going to deal with them both at the same time. Their combined thickness is 0.75. All right. So knowing that, the volume is pi 2 squared, pi r squared, thickness 0.75, times our 90 over 32.2, we get 26.34 slugs. Okay. Then we take this 1/2 times the slugs, the mass, times r squared, which is 2. We get 52.7 slug foot squared. Now keep in mind, this, when we go to do all of our addition, adding the parts up, this is actually subtracted off. Okay, last we have our screw holes, bolt holes. So 4 little holes here, radius 0.25. So we look here, so the thickness is 0.25 and the radius is 0.25. So the volume of every little hole is pi 0.25 squared times 0.25 for thickness times 90 over 32.2. And we'll notice these are all the same distance out. So I'll just take that. That becomes 0.137 slugs, which I'll multiply by 4 because there's 4 holes. All right. Now, so that's the total mass of all the holes. All right. Now I got to convert this into mass moment of inertia. All right. So this is a very important point here. We want to make sure we get this right. We need to move these. All right. We're going to compute the inertia at the center of the hole, its centroid. But we then need it to be relative to the center of the overall thing. So we start from its center and we move it to the center of the overall device it's a part of. So here we have mass moment of inertia. For each hole, 1/2. Mass is 0.137 slugs. R squared, 1/2 mr squared, 0.25 squared. And then we move it over to the center of this device. So the mass, 0.137 slugs. And then we move it a distance 1 foot to get it over into the center. Square that. Then I bracket that, and I multiply it by 4 because there's 4 holes. Overall, that's 0.057 slug-foot squared. All right. Given that, we'll note we can take the mass and subtract off these masses, and so the total mass is 27.99 slugs. And the mass moment of inertia about the center is the big one minus this, minus the bolt holes. And we get 118.3 slug-foot squared. And for educational purposes, we said we want to move it from here to there. So that's straightforward. To go to this one, it's simply what it is at the center, which was 118.3 plus mass, 27.99. Distance squared from here to there is 2.5. Multiply it, add, we have 293.2 slug-foot squared. And that finishes up what we're going to be doing for composite parts. You'll have some more problems with homework and whatnot. Catch you later.